We're going to consider the region of the space enclosed in the first quadrant by y equal x and y equals square root of x. Calculate the volume of the region revolved around the y-axis. Now, in other examples, we did it around the x-axis revolution, and we also just found the area of the space itself. Now we're going to do it slightly different, revolve it around the y-axis. Again, and I can't stress this enough, you need to draw a picture every time. If you want, just pause the video right now and draw your own picture and see how it compares to mine. So to draw the region that's given to us, the graph of y equal x bisects the first quadrant. It goes through the point 1, 1. And y equals square root of x looks like this. So this is y equals square root of x, y equal x. They go through the point 0, 0, they share, and they share the point 1, 1. Now we're going to rotate this region here around the y-axis this time, so it's rotating this way. So if I'm going to draw kind of a picture of what it's going to look like, easier said than done. That's like a cross-section of what it would look like. Now I have to slice it so all the slices are pretty much the same shape. If I slice it this way, it'll be all different shapes, and it doesn't work out right. So I have to slice it horizontally here and then calculate the volume of that slice and then add up all the slices in the end. So what will this shape look like when I revolve it? Well, on the outside it'll be a shape of a V, and on the inside it'll be like a curvy little cusp. Kind of a neat looking vase, but generally vases don't have curvy insides, but you know. So we're going to draw the washer, or the slice, which is going to look like a washer. And a washer, again, is a thin disc that has a hole in the center. Now the thickness of this washer is defined by the y-axis. So the thickness here is going to become delta y. Then we have to think about the volume of that particular slice. Now since this is a washer, we have to take the area of the big bit and subtract the area of the hole. Not the area, the volume. Take the volume of the big bit minus the volume of the hole, and that'll give us our volume of the slice. So the volume of the big bit is just a real thin cylinder, which is pi r squared h. That's its volume, but r is the big one, and I have to take away the hole, which is pi r squared h, where r is the small radius. So notice I can factor out a pi and an h, so I'll do that. And I have to take r squared of the big radius minus r squared of the smaller radius. Now if I look at this, the bigger or the outside radius is defined by this function, y equal x. Now, because everything is in terms of y, I have to make sure that the function I put in for the radius r is in terms of y. So y equal x, if I solve for if I solve for x, I get x equals y. So the big radius is y. Now the smaller radius, which is bounded by the y equal x squared, I can't just put y in here, and I can't put x squared in here, but I have to take the function and I have to solve for x. So squaring both sides, I get y squared equals x. So the radius of this inside part is measured by y squared. So this is the outside, which is y, and the inside is y squared. Now the thickness of my washer, we said earlier, was delta y. So now that's going to be the volume of just that one slice, which is what we're worried about right now. Then I have to think about adding up all the slices that I have. So let's see, all slices, y squared minus y to the fourth dy. Now I think about that green triangle. When I first slice at the bottom, y is 0, and then I slice way on the top, y is 1. So my bounds are 0 to 1. And again, this is very easy to integrate. So go ahead and do it. Pause the machine, do it, and then See if you come up with the number 0.4189 cubic units.